Mm. So, good morning. I am Krishna Kumar from Krishna's Classroom. We continue with our discussion on the topic analysis on R. This is the ninth episode. And in this, we look at the linear space of all linear transformations from Rn to Rm and endow it with a norm, a natural norm, so that it becomes a normal linear space. Okay? So we will explore this first. So what you have is this. You have Rn, Rm. Rn is the domain space, Rm is the range space. Now T is a linear transformation from Rn to Rm. That means T belongs to all linear transformations Rn. And you know that L, Rn, Rm is a linear space over R. Now let us first resolve what the dimension of the space is. I mean, this I have already done. Now if you define a basis, say Vi now this is of course Ei is equal to the collection delta I1 In. Here Ej is equal to now each one written as a column vector is a so here I write the Vi as J1 you know that this is a column vector n rows and n rows and one column. This is m rows and one column. Now each form a basis for R. Now we define P from in fact we define a class of operators in this fashion. P and J contained in L such that Tij Ei Ej okay. I running from 1 n, j running from 1. So altogether there are mn elements Now one can show that, so prove that this collection is a linearly independent set and spans LR and R. So this is a basis, hence and hence the dimension of now we look at a simple example. I leave it you to prove this. This I leave it as a problem. Okay. So let me write. So let consider LR. Now on this we give a basis. So we give a matrices. We define A11 as A12 as and A22 now suppose you take a 2 by 2 matrix A belonging into now let 2 by 2 matrix. Then it's easily verified that A is equal to A2. So it spans, hence it spans now we have to show that this is linearly independent. To show that it is linearly independent, we say A11 0 matrix, that is a linear combination vanishes, implies A11 equal to 0. A22 0. Here you can easily check the following, that is AIJs that is the column matrix corresponding to that. Let's check this. A11. Okay, A11 is quite easy. So A12, let us check A12 is what? Zero, 1, 0, 0. A1 to E1 equal to no, I'm sorry, I think I have to define this. No, I think I have to change here. So I have to, the definition is not complete. Okay. I define this as follows. P11 E1 equal to E complete. Ej Ej equal to Ej so you define it. Okay. So this is how you define it. Or possibly this is the definition. Dij equal to delta okay. Check this. This is the definition. Sorry. Okay. So you can verify this. So, you verify. And this collection forms a so Tij is well defined because you are defining it for all I, J and K. So K is running from, so you see that okay. So you can verify this. I'm sorry about that mistake. Correct yourself and you check whether this is right or not. Otherwise, you may have to do a little bit of correction. Anyway, Lrn is a vector space over R of dimension n. Now we have already introduced the concept of norm on Rn and Rn. Okay. Therefore, through this we will try to introduce a norm on L. How do we do this? Okay, we define the form. Norm of T, this you define as supremum of norm of X. We are using two norm all through equal to 1 of T X, which is the two norm on. Now if you want, you can use here, this is the norm on Rn, this is the norm on Rn. I mean, I think that is clear from the context, because Tx is in Rn, X is in Rn, therefore you are talking about the L2 norm in Rn here and the L2 norm in Rn here. So I am not going to do this. So this is the definition. Whatever this number comes out to be, we define it. Now we have to check whether it is a norm or not. Okay, so that's our next task. By definition, norm of equal to 0. If norm of T is equal to 0, then norm of Tx2 equal to 0 for every x with norm 2 less than or equal to 1. Therefore, you see that norm of Tx equal to 0 for norm x less than or equal to 1. Consequently, T being linear, it means Tx equal to 0 for every x, which implies T is 0. That's the first one. The second one is norm of T equal to 0 implies now this is clear, because norm of T equal, I will do the difficult part. Norm of T equal to 0 implies norm of Tx equal to 0 for every x belonging to Rn such that norm of x okay. So that's the implication. But this means that norm that Tx equal to 0. How do you do that? Suppose then psi is equal to some k times norm of psi times whenever psi is not equal to 0. 0. Whenever psi is not equal to 0. For psi equal to 0, p psi equal to 0. So this is revealing there. So we assume psi not equal to 0, and for that you have this. Okay. Now you see that this is equal to, therefore psi is equal to norm by some x such that norm of x equal to 1. Okay. So now let us compute p psi. And you have already seen that Tx equal to 0 for every x belonging to Rn. With norm of 1. Therefore, what does it mean? This means this is equal to. Okay. Therefore, you get t psi equal to 0, which implies now when t equal to 0, so for every psi, t psi equal to 0, which implies t is 0. So that part is taken care of. Now we have to prove a few things like what all things you have to do. You have to prove this, that is t of lambda x. Norm of now p plus s so these two things will prove in the theorem. Okay, so we'll have to prove these results so that it's a norm. Okay, but before we explore and prove that, we will just do the following. Try to understand what exactly is the meaning of the definition of the norm. Okay, so norm P is defined as supremum. Assume this is a norm, or whatever this means, we will try to explore. This is one. So this is the one that we are trying to understand. Okay. So let us take the case n equal to 1. So then you are working on that T is a linear transformation from R to R. T is LR. Therefore, you know that there is a fascinating characterization. This, then T is can be identified by a scalar say alpha. T can be identified by a scalar say alpha, so that now this identification is possible. Therefore, let us explore what is happening. This is your R, and suppose you choose an X. What does T do? T multiplies it by alpha, and I'm taking this to be alpha X. Alpha X may be anywhere here, so I am taking X not equal to 0. Okay? So this is your alpha X. Okay? Now what we are interested in is, suppose you take the unit. This is a unit ball. This is a unit ball in R1. Now what about the mapping of this? If you map this, suppose let us take a specific case, alpha is positive. Alpha is positive and alpha is also greater than 1. Just take this. Then what happens? It goes to, so this point goes to alpha. And this point goes to minus alpha. This goes to minus alpha. Therefore, T max alpha minus alpha to alpha. Okay, so it goes into this interval, so it just stretches it out. Okay, therefore let us compute what is the maximum. So T x norm of that this will be just a modulus. In the one case, this is going to be modulus. Mod x, mod alpha x, this is equal to mod alpha into mod x. Okay? Therefore, supremum of mod x less than or equal to 1 of Tx equal to so that's the norm. So mod alpha is the norm of T. So you see that this is the farthest point that you can have from 0 to this one. That's how symmetrical. Okay, now let us go to the R2. In R2, it is slightly non-trivial, and then but still you get a very good picture of what this norm means. In fact, you would have already convinced that the extremal or the supremum exists on the boundary. That means it is either at +1 or at -1. That is clear. Okay, and no interior point you will have the supremum. And in fact, you see that this is because you talk about this unit ball, because every other point can be reached out because of linearity through point C by a scalar. Okay, fine. What do we have? Now we look at T from let me look at, let the matrix of T with respect to the standard basis be given by the diagonal one, namely say λ1, λ2. I take them as real. Okay. Now let us look at this one. So the mapping is λ1, λ2, 0, x1, x2 equal to x. Okay, and you take the supremum of this over less than or equal to 1 of the norm of this. Norm of this is λ1 square x1 square plus λ2 x2 square. So what is happening? Let us look at the geometry of this. The geometry of this is the following. You are mapping from R2 to R2, taking the unit circle. This is so you are actually looking at the image of this. Okay, and in this case, what is that image? That image is the set of all points in this space, say of the form λ1 x1 plus λ2 x2 for x1 x2 lying in this. Okay, now without loss of generality, let me also assume this λ1 is something λ. Then what do I have? Suppose I take the points and let me take this. This is just for convenience. I'm getting this. Otherwise, what happens? You just freeze or something like that. So it depends on this. Now in this case, what happens? See, you take the point 1, 0. 1, 0 is this. Now what is the image of that? The image of that is essentially what? 1, 0 goes to 1 0 equal to, yeah, this is no matter. This is equal to, say x1 equal to 1, so it is lambda 1 square to the power half, therefore it is actually lambda 1. Okay, so it goes to some, so if both lambda 1 and lambda 2 are positive, so it goes to some point lambda 1 0. Okay. Similarly, for T of this is what happens. I mean, this goes to this goes to some point zero lambda. Okay, and in fact, it is quite easy to show that this is equal to, this region gets mapped to a region like this. Fairly symmetric because of this. So you take any x1, x2 here, you can show that it goes some point over here. Okay? It's an ellipse. So the circle here. Because you can write this as, see, you can, an arbitrary point on this is an arbitrary point now T of is actually, you write this as a column vector and multiply by this matrix, so this is lambda 1 cos theta that's a T now. Now what is the norm of this? The norm of okay. So you find out where this lies. Now you see that when theta equal to 0, when theta equal to 0, you are going to lambda 1 0. Sorry, when theta equal to 0, then you are taking this point. When theta equal to pi by 2, then you are taking this point 1 0. Sorry, 0 1. 0 1 gets mapped to mod lambda 2. Okay, so it just scales it up like that. Now we have taken both lambda 1 and lambda 2 positive and also taken this, and then this goes to minus lambda 1 0, and this point goes to 0 minus lambda. This is the map for this. Now in between, it will just make lambda 1 cos theta plus lambda 2 sin theta, and then find out what is the locus of that function. When x1 square plus x2 square, when theta goes from 0 to pi, what is the locus of this point? Suppose you take x or y1 equal to lambda 1 cos theta, lambda y2 equal to lambda 2 sin theta. So you have y1 square, y1 by lambda 1 equal to cos theta, y2 by lambda 2 equal to sin theta. Now eliminate theta between these two. So you get y1 by lambda 1 square because you are using cos square theta plus sin square theta equal to 1. So that's an ellipse. So it just goes over to an ellipse. Okay. And then what is the norm? The norm is the supremum of and that's equal to supremum of less than or equal to 1. This is what? This is and this turns out to be in this case simply. So this is the working of the norm. It's not quite easy to work out the norm in all possible cases. Now let me also do another example. Another example is about projections. So these are all invertible objects that I have. This is an invertible object. Suppose I have a projection. Okay, let us go to the situation. We are taking the unit circle in R2. Now you are talking about a projection. So let x be a point x1, and let this line be this is an arbitrary term. So this line will be a1 x1 plus a2 x2 equal to 0. Okay. Now we take another line passing through the origin. This is b1 x1 plus b2 x2 equal to 0. Okay. Now what do I define as projection? The projection is this. Suppose I take an arbitrary point. Okay. And I am going to project, so I am going to project this point to this line along this line. Not taking out of it. I draw this. The picture is this. It's a nice example. I take this line L1 and this line. There are two lines. So this is R. This is A1 x1 plus A2 equal to 0. This is B1 x1 B2 equal to 0. I also assume A1 A2 B1 B2 is not equal to 0. That means these lines L1 and L2 are independent. Now I take an arbitrary point here, x. What is the projection? Now let me define the projection as, so let me write down P L1 L2 as the projection of onto L1 L2. What is that? I take this as a diagonal vector, complete the parallelogram with this as a diagonal and the sides on this. So what do? I draw a line parallel to this. I draw a line parallel to this. Okay. So this is your PS. This is the vector x. Now if you choose a vector here, suppose your x is here, then what you do? What is the projection that you do? See, you draw a line parallel to this. You draw a line parallel to this one. So you have a parallelogram, and this is the okay. This is a parallelogram. Therefore, this is suppose this is y, this is d. Okay, so y gets mapped. So you see that all the points in this space are mapped only to this line. Okay, according to this rule. Okay, so all the points in this plane are mapped onto this line L1. So range of equal to the line L1. And you see that nullity of null space of that is all the points on this line gets mapped to 0. So this is about the projection. Now let us try to compute the norm. Okay. Now where does the point get mapped to? Any point here goes to this one, this line. So this is your L1, this is your L2 only. Okay. Now let us see what happens to the points here. Where does it go to? What you do is you draw two lines parallel to L2 which are tangential to the unit point. Okay. L2. Now find out where it really goes to. It goes to this C. So you see that now it is clear. All the points on this are mapped on this in this way. This is how the mapping takes place. And where do these points lie? These points lie here. So you see that it lies between, it is on this portion. See, the image of the projection is on this point. Okay? Because what happens is any point you take here, so where does it get? Okay. Any point you take here, where does it get? You travel parallel to L2 and see where it meets this line. You just don't go beyond these points on this line. Okay? Therefore, what is the norm? The norm is in fact this is symmetry. So the norm is this norm of L1 L2 and this is the supreme of norm of P L1 L2 of X. This is this. Whatever be the length that you get is going to be the norm. Okay? You got a beautiful idea of what it is? Okay. Right? That's about the projection. Therefore, the length of OP. So you draw. Let me just repeat. Okay? I have L1 here, I have L2 here. L1 and L2 are not identical, that means they are not incidental except at the point 0, 0. They are independent. That is guaranteed by choosing A1, A2, B1, B2, the determinant of this is not equal to 0. Now you take an arbitrary point here. The arbitrary point is projected. What is the projection? The projection is to L1 along L2. That is what I denote by P L1 L2. So P L1 L2 of X is this point. This point is this. So this is the map P L1 L2. Okay. So any point you take, for instance, you take the point here. This is map. You walk parallel to this, and then find out where you reach, and that's the point. So this is what you call. So if you take a point here, what you do is you walk parallel to L2 and see where you meet L1. So this is the point. So this is Z, and this is P, L1, L2. This point is this is the map. Now what we want to work on is to identify the range of P, L1, L2 when you conform yourself to the unit circle. The unit circle is this, or the unit disk is this. Looking at the image of this. The image of this will go where? How do you do? Take any point on here and try to map it here. Also this one. Okay, this one goes to this, 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 and so on. Similarly, any point here goes to this, any point here goes to this, and so on. So this is how the mapping takes place. So what I am doing is I am drawing the two tangents to the circle which are parallel to the lines L1, sorry, the lines L2, and then find out where those lines meet the line L1. You see that it's clear that every point in this disk gets mapped into the interval I have marked in the yellow on the line L1. Okay. Now I can calculate this. Okay. So this point I call norm of P L1 L2, and this is equal to supremum of this one. So supremum is actually you are taking the distance of the point, that is the maximum distance that you have on the image of the unit circle is what you call the norm. So the norm of P is the maximum distance a point has, a point in P of the unit circle disk or unit ball this is what you call the norm. Okay. So I hope you got a geometric idea of what it is. Right? Now here you see that because it's a projection, it maps on a line. Whereas here, since you have assumed you have taken any general map, then it goes to some set. The earlier example that we took, the unit ball goes to a sort of ellipse. The unit ball goes to an ellipse because it will be x square by a square plus y square by b square equal to 1. Okay, then that gives the norm is essentially given by the maximum of lambda 1, mod lambda 1 and mod lambda 2 in that case. So in every case, this is this is not the point what exactly is this, but the norm is very different. Okay. Now we have not shown that this gives a norm because we have to verify each one of these points. Okay, let me see how we do it. I think I think you got an idea of what it is. Now let us work on this. I hope the image is very clear. But one exercise that one should do is compute the projection of arbitrary point projection of vector on R2 in R2, which is a projection onto the line equals 0, where okay, it's a good exercise. First you try with some numbers here, say something like projection onto, for example, say A1 equal to 1, A2 equal to 1. And then you take D1 equal to minus 1, B2 equal to 1. Okay. Find out what is the projection, or you take some other numbers like 2 and 1. Something like that. These two are linearly independent vectors. Okay, so this condition is satisfied. So find out what is the. This is a good exercise. I think if you do this, then you will get the hang of the whole lot of things. Right? So in general, we prove the following theorem. So let us prove the following theorem. That means you are proving this is a linear transformation. So if A belongs to L, Rn, then norm A is finite. So also A uniformly is uniformly continuous on That's the first theorem. Okay, let us prove this. What about the proof? The proof of this is, so let determined if you say what AE1 is, say what AE2 is, etc., what AEN is. So let X be equal to sigma Cj Tj. Now suppose you take norm of x2 is less than or equal to 1, implies mod Cj is less than or equal to 1 Fdj. This is clear. This is obvious because what you get, okay, see that if the norm of this is so, then this is what you have, C1 square plus less than or equal to. This is the norm of, this is the norm of x. This is equal to this. And this is less than or equal to 1 means each one of mod Cj is less than or equal to 1. So that is there. Now what is the implication? Therefore norm of Ax, which is equal to norm of sigma Ci A EI. And this, you know, is less than or equal to summation over mod Cj norm of here. And this, you know, is less than or equal to norm of summation over I norm of A. And what is AEI? AEI, EIs are fixed vectors. So AEI, AE1, AE2, etc., AEN is are vectors, n vectors in Rn. Okay? Therefore, their norm is the norm of AEI is a fixed number. So it's a finite set of numbers that you have which is bounded. Therefore, this is finite. Okay. Therefore, what you have? Norm of A of x and this is finite. So A is bounded. It is bounded by this number. Whatever be the A, you calculate AE1, AE2, AEN, compute their norm. It's a finite set of numbers, and then take the sum of them. It is going to be a finite number, and that is going to be the bound for that. Okay. Right. Now we calculate this is the image. AX and AY are the images of this. Now we estimate the norm of this. This is less than or equal to norm of A into norm of X minus Y. And this is less than or equal to this is what you get. Okay, this is a number. So this is something like, that means this is something like this: AX minus AY is less than or equal to sum M times norm of X minus Y. Okay. See, this is the distance between AX and AY, the image points. And this is the distance between X and Y. So this is the distance between AX and AY, this is the distance between X and Y. So as X goes to Y, AX goes to AY. Let's continue with it. Or you can easily work out given epsilon. Then X is delta equal to, what is it? Epsilon by M. It's that norm of so for arbitrary choice of epsilon, there exists a delta such that this. And also you see that once epsilon is given, delta depends only on epsilon, not on X and Y. Okay, therefore it shows that the continuity is uniform continuity. Okay, so I think I'll stop here. Yes, it's quite late.